Find somewhere comfortable tonight. You don't need to follow any of this closely. You don't need to remember a single word. If you drift away somewhere in the middle, that is exactly the right thing to do. Just let the words come and go like something heard from another room. A quiet voice, a little warmth, nothing that asks anything of you. Tonight, we are going somewhere cold and still and ancient. We are going to the ice. Not the ice in your glass, not the frost on a winter window, but something far older and far heavier than either of those. We are going to the places on this earth where snow has been falling for so long and piling so deep that it has slowly, over centuries, turned into something else entirely, something that moves. Something that carries the memory of the air that was breathed 10,000 years before any of us were born. Glaciers, rivers of ice, the slowest, most patient rivers on the planet. If you have ever seen one, stood at the edge of one, or even just seen a photograph, you will know that they look utterly still. They look like something that has always been exactly where it is and always will be. But that stillness is an illusion. Beneath it, something is happening, has always been happening. The ice is moving, grain by grain, molecule by molecule, in a slow and ancient conversation with gravity that has been going on since long before any human being thought to look. We are going to follow that conversation tonight, from its very beginning, from a single snowflake falling in the cold mountain air, all the way down to the sea. We are in no hurry. The ice certainly isn't. It begins with a snowflake, which is itself already a small wonder. A snowflake forms when a water molecule, two hydrogen atoms bonded to one oxygen atom, a shape like a tiny bent arm, encounters a dust particle high in the atmosphere and begins to crystallize around it. Water molecules, as they freeze, arrange themselves into a hexagonal lattice, a six-sided structure, because of the particular angle at which the hydrogen atoms bond to the oxygen. That hexagonal symmetry propagates outward as the crystal grows, and because each arm of the growing flake encounters slightly different conditions of temperature and humidity as it falls, no two arms grow in precisely the same way. The result is that intricate, branching, six-fold symmetry that we recognize as a snowflake. It is a molecule's geometry, written large enough to see. That snowflake falls. It lands on a mountainside, somewhere high enough that the winters are long and the summers are short and cool, perhaps in the Alps or the Himalayas or the ranges of Alaska or on the vast white plateau of Antarctica. It lands among thousands of other snowflakes, and together they form a layer of fresh snow, light, airy, roughly 90% empty space because the crystals are so delicate and branching that they cannot pack closely together. And then the winter passes and summer comes, and here is where something important happens. The snow does not entirely melt. The mountain is high enough or the latitude far enough north or south that the warmth of summer is not quite sufficient to undo what the winter built. A little snow survives, a thin layer preserved. The next winter buries it. And the winter after that buries that. Year by year, the layers accumulate, and as they do, the snow at the bottom begins to change. This is where the transformation begins, and it is worth following it carefully, because it is one of the most gradual and profound metamorphoses in nature. Fresh snow crystals are those delicate, branching stars, but they are not stable in that form, even well below freezing. The outermost tips of those branches, the finest, most exposed points, are at a slightly higher energy state than the flat faces of the crystal. In physics, a surface that curves sharply outward has a higher vapor pressure than a flat surface, meaning it loses water molecules to the surrounding air more readily. Those molecules drift through the tiny air-filled spaces between crystals and redeposit somewhere flatter, somewhere lower. Energy. The sharp tips slowly blunt, the delicate arms retract. The crystals round off into small, granular spheres, and in doing so they pack together more tightly. This rounded, granular snow is called firn. It is the halfway state, no longer fresh snow, not yet ice, and it is recognizable if you have ever dug into a deep snowpack and found that old, sugary, slightly crunchy layer beneath the fresh surface. That is firn. It is typically around 50 to 60% ice by volume, with the rest still open, pore space filled with air. But the transformation continues. More snow falls on top. The weight increases. The pressure on the firn below begins to squeeze those granular grains together, forcing out the air between them. The grains deform slightly at their contact points, and the boundaries between individual crystals begin to be erased as the molecules at those boundaries migrate and merge. The grains interlock. The pore spaces shrink, and many of them close off entirely, trapping whatever air was inside them as tiny sealed bubbles. This process takes time, real time. In the cold, dry conditions of central Antarctica, where very little snow falls each year and temperatures are extreme, it can take 1,000 years for firn to complete its transformation into glacial ice. In the warmer, wetter conditions of a temperate mountain glacier, where more snow falls and surface melting and refreezing accelerate the process, it might take only a few decades. But in either case, what is needed is roughly 50 meters of accumulated firn pressing down from above before the density increases enough and the pore spaces close enough for true glacial ice to form. Glacial ice, when it finally arrives, is a different substance from anything you encounter in daily life. It is dense, around 917 kilograms per cubic meter, compared to liquid water's 1,000. It is blue in the deep interior, because the ice is so pure and so thick that it absorbs the longer red wavelengths of light and transmits the shorter blue ones. And it contains, sealed within it, those tiny trapped air bubbles, each one a perfect airtight sample of the atmosphere at the time it was enclosed. A bubble from deep in an Antarctic ice core might hold air that last moved freely in the world 800,000 years ago, before our species existed. The oxygen inside it was breathed by no human lung. It is ancient atmosphere preserved in ice, waiting. The ice is also by now under considerable pressure. The weight of 50 or 100 or several hundred meters of ice and firn above is enormous, and it is here, under this patient, accumulating weight, that something begins to stir. Ice, under sustained pressure, does not simply sit still. It deforms, it flows, not quickly, not in any way visible to someone standing beside it on a given afternoon, but measurably over weeks and months and years. The whole mass of accumulated ice begins, almost imperceptibly, to lean. Gravity, which has been waiting all this time with the patience that only physics can manage, begins its work. A glacier is being born. The region where snow accumulates faster than it melts is called the accumulation zone, and it sits at the top of the glacier, usually at higher elevation. Below it, lower down the mountain where temperatures are warmer, lies the ablation zone, the region of loss where ice melts away in summer faster than new snow can replace it. Between them, somewhere in the middle, is the equilibrium line, the invisible boundary where gain and loss exactly balance. Above it, the glacier grows. Below it, it wastes away. And through the whole system, from top to bottom, the ice flows. Slowly, continuously, driven by the weight of everything above. That flow, how it actually happens, what is occurring inside the ice at the level of individual crystals and molecules, is one of the quieter marvels of earth science. But before we go there, it is worth pausing on the human story. Because for most of history, no one believed the ice moved at all. In the summer of 1827, a Swiss professor named Franz Josef Hugi did something that seems, in retrospect, almost comically simple, and yet no one had thought to do it properly before. He walked out onto the surface of a glacier in the Swiss Alps, the unhurried Glacier, a long tongue of ice descending through a deep valley in the Bernese Oberland, and he drove a series of wooden stakes into the ice. He noted their positions carefully, relative to fixed points on the surrounding rock walls of the valley. And then he walked away. He came back the following year, and the year after that, and what he found each time was that the stakes had moved, not a little, substantially. They had crept downhill toward the lower end of the glacier at a rate of around 1 meter per day in the faster central sections. Hugi had done something quietly revolutionary. He had proven, with simple wooden stakes and patient observation, that a glacier is not a static body of frozen water. It moves, it flows, it is, in the most literal sense, a river, just an extraordinarily slow one. The man who picked up Hugi's work and ran with it, who turned those preliminary observations into a full scientific program, was Louis Agassiz. And Agassiz is a figure worth spending a moment with, because his story is one of the great examples of a scientist being simultaneously profoundly right and, in other parts of his thinking, deeply wrong. A reminder that brilliant minds are not uniformly brilliant and that we should hold the ideas, not the person. Agassiz was Swiss-born, a naturalist of extraordinary energy and ambition. In 1837, when he was 30 years old, he stood up before the Swiss Society of Natural Sciences and proposed something that his audience found, to put it gently, difficult to accept. He proposed that the Earth had, in the not-so-distant geological past, been covered by vast sheets of ice, not just the mountain glaciers visible in the Alps, but enormous continental ice sheets stretching across Europe and North America, grinding the landscape flat, depositing boulders far from their origins, carving the valleys and lakes and fjords that we now take to be simply the natural shape of things. He called it the Ice Age. The Eisheit. The reaction was largely one of polite skepticism shading toward exasperation. The idea seemed too large, too wild. The great geologist Charles Lyell, whose influence on the field was immense, was unconvinced. Others suggested the displaced boulders, the erratics, the geologists called them, rocks sitting in the middle of plains, entirely unlike the local stone, had been carried by floods or by floating icebergs or by any number of mechanisms that did not require imagining all of northern Europe buried under a kilometre of ice. Agassiz, undeterred, went to the ice. He established a research station on the unhurried Glacier, a rudimentary hut built on a large boulder on the glacier's surface, which he called the Hôtel des Neuchâtelois. He and his colleagues camped there through multiple summers in the 1840s, measuring, drilling, observing. They drove stakes in lines across the glacier's width and watched them spread apart over time, confirming that the ice in the center moved faster than the ice at the edges. They bored holes down into the ice and found that the glacier moved faster at the surface than at depth. They mapped moraines, those long ridges of rock and gravel pushed up at the edges and fronts of glaciers, and recognized them as evidence of past positions, past extents, a kind of geological memory of where the ice had been. But Agassiz was not alone in watching the ice, and the question of how it moved, not just that it moved, but what mechanism propelled it, was being pursued simultaneously by several people in a way that would eventually lead to a painful and rather undignified dispute. One of those people was a Scottish physicist named James David Forbes. Forbes was a careful, meticulous man, and he had been watching glaciers in the French and Swiss Alps since the late 1830s. He was struck by something that Agassiz's measurements had also suggested. The glacier moved exactly like a river. Not just in the obvious sense of flowing downhill, but in the detailed structure of that flow. The center moved faster than the edges. The surface moved faster than the base. These were precisely the velocity patterns you would see in a river of water, where friction with the banks and the riverbed slows the water nearest to those surfaces, while the central, unimpeded water flows most freely. Forbes concluded that ice must behave under the sustained pressure of its own weight as something like a very viscous fluid, not a rigid solid that slides as a block, but a substance capable of continuous internal deformation, of flowing through itself the way honey flows, or pitch, or glass over very long timescales. He called it the viscous theory of glacier motion. Around the same time, a bishop in Savoy named Louis Rendu had arrived at a remarkably similar conclusion through careful observation rather than formal measurement. In a book published in 1841, Rendu described the glacier as behaving like a viscous body, noted the faster motion at the center compared to the edges, and drew the analogy to a river explicitly. His work was written in French and initially received little attention outside the Alpine region, but the observation was there, clear and precise, predating Forbes's formal measurements. The dispute between Forbes and Agassiz over priority, who had contributed what, who deserved credit for which insight, grew bitter and complicated, as such disputes in Victorian science often did. It need not detain us too long here. What matters is what they collectively established. Ice is not a rigid solid. It flows internally. And that flow follows patterns that are recognizable from the behavior of viscous fluids, even though ice, touched with a finger, is undeniably hard. The why of that, the mechanism beneath the observation, would take another century to fully work out. In the early 1950s, two researchers gave the viscous theory its mathematical foundation. John Nye, a British physicist working in Cambridge, derived a mathematical description of how a glacier should flow, given its geometry and the properties of ice, treating ice as a non-Newtonian fluid, a fluid whose resistance to flow changes depending on how hard you push it, rather than remaining constant the way water's does. And James Glenn, also British, took blocks of ice into a laboratory and actually measured how they deformed under controlled loads, confirming experimentally what Nye's theory predicted. Together, their work produced what glaciologists now call Glenn's flow law, a relationship between the stress applied to ice and the rate at which it deforms, and it remains the quantitative backbone of glaciology to this day. Centuries of patient watching, stakes in ice, lines of boulders, moraines on hillsides, had become precise science. The glacier had been read, at last, not just as a landscape feature, but as a physical system governed by laws that could be written down and tested. What those laws describe, at the level of the ice crystals themselves, is a story stranger and more beautiful than Forbes or Rendu could have known. Here is the thing that takes a moment to really absorb. When a glacier flows through internal deformation, the ice does not melt. It does not become liquid, even briefly. It remains solid throughout, and yet it flows. It changes shape. It moves. Solid ice, flowing like a liquid, without ever ceasing to be solid. This seems, on the face of it, impossible, and yet it is happening right now in every glacier on Earth. To understand how, you need to go inside an ice crystal, not to the scale of snowflakes, but smaller, to the scale of the individual water molecules and the lattice they form. Ice, in its most common form, is a crystal. Its water molecules are arranged in a repeating, orderly pattern, that hexagonal structure we mentioned earlier, each oxygen atom bonded to 4 hydrogen atoms in a tetrahedral arrangement, the whole thing extending outward in a regular lattice. In a perfect crystal, every molecule would be exactly where the pattern dictates. But real crystals are never perfect. They contain defects, places where the pattern is interrupted, where something is missing or slightly out of alignment. One of the most important types of defect is called a dislocation. A dislocation is a line defect. Imagine a plane of molecules within the crystal that is 1 row shorter than the planes above and below it, so that along the edge of that short plane, the molecules on either side are slightly misaligned, slightly strained. The crystal is not broken at that line, but it is under local stress. And that local stress has a remarkable consequence. It makes the dislocation mobile. When an external stress is applied to the crystal, the weight of ice above pressing down, gravity pulling the whole mass downhill, the energy of the system is reduced if the dislocation moves. And it can move relatively easily because it does not require all the bonds across an entire plane to break simultaneously. Instead, the bonds break and reform one row at a time as the dislocation migrates through the crystal. Think of it like moving a heavy rug across a floor. Instead of lifting the whole rug and dragging it, you make a small fold at one end and push the fold across the rug. The fold, the dislocation, travels easily, and when it reaches the other side, the rug has shifted by exactly one fold width. The effort required is far less than moving the whole rug at once. This migration of dislocations through ice crystals under sustained stress is called intracrystalline gliding. It is the primary mechanism by which individual ice crystals change shape without breaking. One layer of the crystal shears past another, driven by the dislocation moving through. And because a glacier is made of countless millions of such crystals, all deforming in this way under the weight of the ice above, the whole mass flows. But there is more happening than just dislocation movement within individual crystals. At the boundaries between adjacent crystals, the grain boundaries, the surfaces where one ice crystal meets its neighbor, something else occurs. The molecules at a grain boundary are in a slightly disordered state, not quite fitting the lattice of either crystal perfectly. This disorder gives them a higher energy and greater mobility than molecules deep within a crystal. At temperatures close to the melting point of ice, this boundary region becomes almost fluid-like. Not truly liquid, but with molecular mobility that is significantly higher than the crystal interior. This thin, mobile zone acts as a kind of internal lubricant, allowing adjacent crystals to slide past one another at their shared surfaces. This second process, crystals sliding past each other at their boundaries, is called grain boundary sliding. It complements the internal dislocation movement, and its importance varies with conditions. In finer-grained ice, where the total area of grain boundaries relative to the volume of ice is higher, grain boundary sliding contributes more to the overall flow. In coarser-grained ice, dislocation movement within crystals dominates. Now, Glen's flow law brings all of this together into a single quantitative relationship. The law states that the rate at which ice deforms, the speed at which it strains under an applied stress, is proportional to the cube of that stress. This is a non-linear relationship, and the non-linearity has profound consequences. If you double the stress on a piece of ice, it does not deform twice as fast. It deforms 8 times as fast. 2 cubed, triple the stress, and the deformation rate rises 27-fold. This means that small increases in the thickness of a glacier, which increase the pressure and therefore the stress at the base, can produce very large increases in the rate of flow. Thin ice barely flows at all. Thick ice flows with a speed that grows rapidly as thickness increases. Temperature matters enormously too. The parameter in Glen's flow law that captures the ease of deformation, essentially how readily the ice crystals accommodate the applied stress, is exquisitely sensitive to temperature. This is because warmer ice has more thermally active molecules, more molecular vibration, more mobility at grain boundaries, more opportunity for dislocations to move. Cold ice, deep in Antarctica at -40 or -50 degrees, flows with almost geological slowness. Ice at -5, approaching its melting point, flows with a freedom that would be visible on a human timescale if you had the patience to watch. This temperature sensitivity also explains why glacier flow is concentrated at depth. The surface of a glacier is cold, exposed to the atmosphere. Deep within the glacier, closer to the base, the ice is warmer. insulated by the ice above it and receiving heat from the earth below. The warmest, most easily deformed ice is at the bottom, so the rate of internal deformation increases with depth and the glacier moves fastest at its surface. Exactly what Agassiz and Forbes observed, confirmed now by the physics of molecular defects. There is one more process worth understanding: recrystallization. As ice deforms, the individual crystals are not passive passengers, they are constantly changing. Crystals that are poorly oriented relative to the direction of applied stress. Crystals whose internal lattice planes are at an awkward angle for gliding are harder to deform, and they tend to be consumed. Their molecules migrate across grain boundaries to feed adjacent, better-oriented crystals which grow. Over time, the ice develops a preferred crystallographic texture, most of the crystals oriented with their easy glide planes aligned with the direction of shear. The ice becomes, in a sense, better at flowing the longer it flows. It optimizes itself. And so a glacier, at its deepest level, is a community of crystals in constant, slow negotiation, growing, shrinking, reorienting, slipping past each other along boundaries lubricated by near-liquid molecular layers, each one moving its dislocations through its lattice, one careful step at a time. The whole vast, blue, ancient mass of it is the sum of those molecular conversations accumulated over decades and centuries. It flows without melting, solid and yet river-like, patient and yet inexorable. This internal deformation, this creep, as glaciologists call it, is one of the 2 or 3 fundamental mechanisms by which glaciers move. But for many glaciers, particularly those resting on rock at temperatures near the melting point, something equally important is happening at the very base of the ice, in the invisible zone where glacier meets bedrock. The base of a glacier is a place no one has ever stood and looked around. It is dark, and it is under immense pressure, and it is, in the right conditions, wet. That wetness is the key to something remarkable. To understand why the base of a glacier can be wet even when the ice above is well below 0 degrees, you need to know something interesting about the melting point of ice. For most substances, pressure has a relatively small effect on the temperature at which they melt, but ice is unusual. Because ice is less dense than liquid water, because the hexagonal lattice of ice takes up more space than the disordered arrangement of molecules in liquid water. Applying pressure to ice tends to encourage it to collapse into the denser liquid phase. In other words, pressure lowers the melting point of ice. This is a direct consequence of the same molecular geometry that makes ice float. The open hexagonal lattice, held apart by the angle of the hydrogen bonds, is larger and less dense than liquid water. Squeeze it hard enough, and the energy cost of maintaining that open structure becomes too high, and the lattice collapses into liquid. The greater the pressure, the lower the temperature at which this happens. The numbers are modest but consequential. For every additional atmosphere of pressure, roughly the pressure of another 10 meters of water, or a similar depth of ice, the melting point of ice decreases by about 7/1000ths of a degree. But a glacier 300 meters thick exerts a pressure at its base of roughly 30 atmospheres above the pressure at the surface, which depresses the melting point by about 1/4 of a degree. A glacier, a kilometer thick, depresses its own melting point at the base by close to 3/4 of a degree. This is enough. In many glaciers, particularly in temperate mountain regions where the ice is not extremely cold to begin with, the combination of the pressure from above and the gentle heat rising from the Earth's interior is sufficient to bring the temperature at the glacier's base right to the pressure-adjusted melting point. The ice at the very bottom just barely melts. A thin film of water forms between the ice and the bedrock. And that film changes everything. Water is an extraordinarily effective lubricant. Even a layer just a few millimeters thick, or in some cases micrometers, between the base of the glacier and the rock beneath it dramatically reduces the friction that would otherwise resist the glacier's motion. The whole mass of ice, kilometers wide and hundreds of meters deep, rests on this thin, wet skin and slides. This is basal sliding, and in temperate glaciers, the kind found in the Alps, in Patagonia, in New Zealand, in coastal Alaska, it can account for the majority of the glacier's forward movement. Internal deformation is happening too, but the sliding at the base contributes more to the overall speed. The heat that sustains this basal melt comes from two sources. One is geothermal heat, the slow, steady warmth rising from the Earth's interior where radioactive decay in the mantle and crust releases energy continuously. This geothermal heat flow is small, only about 60 to 90 milliwatts per square meter. In most continental regions, enough to slowly warm the base of a thick ice sheet over thousands of years, but not enough to melt ice rapidly on its own. The other source is frictional heat, generated by the sliding itself. As the glacier moves across the bedrock, friction converts some of the kinetic energy of that movement into heat, right at the interface where it is most needed. The faster the glacier slides, the more heat is generated, which lubricates the base further, which allows the glacier to slide faster still. It is a feedback loop, self-sustaining, the glacier in a sense warming its own path. But the bedrock beneath a glacier is not smooth. It is rough, fractured, mountainous at the small scale, covered in bumps and ridges and protrusions of all sizes, from boulders to minor ripples in the rock surface. And here is where one of the most elegant and counterintuitive processes in glaciology comes in. It is called regulation, a word that means, roughly, refreezing, and it is the mechanism by which a sliding glacier navigates the obstacles in its path. Imagine the glacier encountering a protrusion in the bedrock, a rounded knob of rock, perhaps half a meter high, sticking up into the base of the ice. As the glacier pushes forward, the ice on the upstream side of the knob is pressed against it. The contact pressure between the ice and the upstream face of the knob is higher than the pressure in the surrounding ice. And because pressure lowers the melting point of ice, the ice in contact with the upstream face of the knob melts, even though its temperature has not changed. It becomes water. That water, under the slightly higher pressure on the upstream side, flows around the knob through the thin film at the ice rock interface, moving toward the downstream side. On the downstream side of the knob, the ice is in the knot's shadow, protected from the glacier's push. The pressure there is lower. The pressure melting point rises again. The water, finding itself at a temperature below its new, higher melting point, refreezes. It becomes ice again, welding itself to the downstream face of the knob. The glacier has, in effect, passed through the obstacle. Ice melted on one side, flowed around as water, and refroze on the other. The knob has been navigated without the glacier ever having to deform around it, though deformation helps with larger obstacles where regulation alone is insufficient. This process, melt, flow, refreeze, happens continuously across the entire base of a sliding glacier. At every small obstacle in the bed. It is happening right now, in the dark and the cold and the pressure, in places where no human eye has ever looked. A quiet, perpetual, molecular scale negotiation between ice and stone. The regulation process is most efficient for small obstacles, those less than roughly a meter in diameter. For larger obstacles, internal deformation of the ice takes over. The ice flowing around the bump by the dislocation, migration and grain boundary sliding mechanisms we explored earlier. In practice, both processes operate together across the range of obstacle sizes, and between them they allow a sliding glacier to move over a bed that would seem, to a human walking across it, to be formidably rough. What emerges from all of this is a picture of the glacier's base as a place of extraordinary activity, wet, warm by the glacier's standards, constantly melting and refreezing, the ice and the rock in a continuous slow dance. The water that is produced does not simply accumulate without limit. It drains away through channels and films and porous pathways, emerging at the glacier's snout as meltwater streams. But while it is there, at the base, it is doing the essential work of keeping the glacier moving. And in some glaciers, the situation at the base is even more complex than this, because beneath some glaciers, there is not solid bedrock at all. There is something softer and more yielding, and in its own way, even more interesting. Not every glacier rests on bare rock. Some rest on sediment, thick accumulations of the rock flour and gravel and clay that glaciers grind from the bedrock beneath them over thousands of years, mixed with water, compressed and rearranged into a layer that can be meters or even tens of meters thick. Until, under the right conditions, does something that bare rock cannot do. Close. To understand why, consider what till is made of. It is a mixture of rock particles of many sizes, from fine clay particles smaller than 1/1000 of a millimeter to pebbles and boulders, all packed together with water filling the spaces between them. Those spaces between grains, the pore spaces, are crucial. If the water in those pore spaces is under high pressure, if it is being squeezed from above by the weight of the glacier and cannot easily drain away, then something interesting happens to the mechanical behavior of the sediment. Normally, the grains in a sediment are pressed against each other, and the friction between those grain contacts is what gives the sediment its strength, its resistance to being deformed. A dry sand is hard to compress but flows easily because the grains can slide past each other. A wet sand with low water pressure behaves similarly. But if the water pressure in the pore spaces becomes very high, it begins to support some of the weight of the glacier above, reducing the pressure between the grains themselves. As the effective pressure between grains falls, so does the frictional resistance between them. At sufficiently high pore water pressure, the grains lose much of their mutual grip. The till becomes weak, almost slippery, and the glacier above, pushing forward, can cause the till to deform, to shear, to flow slowly forward, carrying the ice above it like a passenger. This process is called subglacial till deformation, and in some glaciers it is not a minor contributor to movement. In some cases, measurements have shown that the deformation of the till layer beneath a glacier accounts for up to 90% of that glacier's total forward motion. The ice itself is barely moving relative to its bed. It is the bed that is moving, carrying the ice along. The conditions required are specific. The till must be saturated with water, and the water must be under sufficient pressure. This tends to occur where the glacier is thick enough to generate significant basal melting, where the drainage of that meltwater through the till is restricted, and where the till itself is fine-grained enough to hold water rather than letting it drain freely. These conditions are met in many places beneath the great ice sheets of Greenland and Antarctica, and they have profound implications for how fast those ice sheets can move. Which brings us to ice streams. An ice stream is not a separate glacier. It is a region within a larger glacier or ice sheet where the ice moves dramatically faster than the surrounding ice, sometimes 10 or 20 or 50 times faster. From above, an ice stream looks like a river within a river, its faster moving ice bounded on either side by slower ice, the boundary marked by intense shearing and fracturing where the two flow regimes meet. Ice streams are the express lanes of an ice sheet, the corridors through which the vast majority of the ice sheet's mass is funneled toward the ocean. And one of the most extraordinary ice streams on Earth is Jakobshavnsbrei, on the western coast of Greenland. Kubshavna, the name is Danish. The glacier itself has a Greenlandic name too. Cermek Kujalek drains a significant portion of the Greenland ice sheet, a catchment area of roughly 850,000 square kilometers of inland ice. For most of its length, it moves at the pace of a typical glacier, a few meters per day, fast for ice but still invisible to the human eye. But near its terminus, where it meets the sea, it accelerates to something that is genuinely remarkable. At its fastest, in recent decades, Jakobshavn has been measured moving at speeds of around 20 to 40 meters per day. In a week, it advances as far as a tall building is high. In a month, it moves more than a kilometer. That speed is the product of several reinforcing factors working together. The glacier sits in a deep trough, a valley carved by the ice itself over millions of years, with its bed well below sea level. The depth of the ice means enormous pressure at the base, generating significant basal melt. The till beneath portions of its bed is saturated and weak, contributing deformation from below. And at its terminus, the glacier flows directly into a deep fjord of relatively warm ocean water, which eats at the glacier's underwater face, a process we will return to later, destabilizing the ice and allowing it to carve, to break apart, more rapidly than it otherwise would. Each carving event removes ice from the front of the glacier, reducing the back pressure that was restraining the flow behind it, and the glacier accelerates forward to fill the gap. The result is a glacier that drains an area the size of a small country, moving its ice to the sea at a pace that contributes meaningfully to global sea level rise. Jakobshavn alone has been estimated to contribute around 4% of total global sea level rise in recent decades. But Jakobshavn is not unique in kind, only in scale and speed. Greenland has many ice streams, and Antarctica has more. Vast corridors of fast-moving ice, some of them wider than whole mountain ranges, draining the interior of the ice sheet and delivering ice to the Southern Ocean. The ice streams of West Antarctica, the Pine Island Glacier, the Thwaites Glacier, the Whillans Ice Stream are among the most closely watched features in contemporary glaciology because they drain a portion of the ice sheet that rests on bedrock below sea level, making them potentially vulnerable to a self-reinforcing retreat that, once started, might be difficult to stop. What these ice streams illustrate is that the simple picture of a glacier as a mass of ice slowly creeping downhill under its own weight is incomplete. A glacier is a system, and the behavior of that system depends on everything: the temperature of the ice, the pressure at the base, the nature of the bed, the geometry of the valley or trough, the temperature of the ocean at the terminus. Change any one of those things significantly, and the whole system can respond in ways that are difficult to predict precisely. The surface of a glacier, meanwhile, is recording all of these internal stresses in a language that, once you know how to read it, is written clearly across the ice. Stand at the edge of a large glacier and look at its surface. What you see, if the glacier is active and flowing, is rarely smooth. The surface is fractured, tilted, heaved into ridges and towers, split by great cracks that plunge into blue shadow. It is a landscape that seems to have been violently disrupted, and in a sense it has been, though the violence has been slow, and the disruptive force is nothing more dramatic than differential motion. The glacier does not move as a single rigid block. Different parts of it move at different speeds. The center moves faster than the edges. The surface moves faster than the base. Where the glacier passes over a steepening in the bed, or rounds a corner, or narrows through a constriction, different portions of the ice accelerate or decelerate relative to their neighbors, and all of these differences in velocity. These velocity gradients, as a physicist would call them, impose stresses on the ice. The ice is being pulled in different directions simultaneously, stretched in some places, compressed in others, twisted where two flow regimes meet. The ice responds to these stresses differently depending on depth. Near the surface, in roughly the top 30 meters, the ice is under relatively low confining pressure. The weight of ice above it is not yet sufficient to squeeze it into the plastic, deformable state that deeper ice occupies. So surface ice is brittle. When a stress is applied to brittle ice faster than the ice can deform to accommodate it, the ice fractures. It cracks. A crevasse opens. Crevasses form where the ice is being stretched, where one part of the glacier is moving faster than an adjacent part, pulling them apart. Where the center of a glacier accelerates away from its slower edges, the surface is stretched transversely, and crevasses open roughly perpendicular to the direction of flow in great curved arcs across the glacier's width. Where the glacier flows over a steepening in its bed, the surface ice is stretched longitudinally, and crevasses open parallel to the flow direction, splitting the glacier into long ridges. Where the glacier rounds a bend, the outer edge is stretched while the inner edge is compressed, and a complex, intersecting pattern of crevasses develops. A crevasse can open to a depth of around 30 meters before the weight of the ice above. The confining pressure becomes sufficient to prevent further fracture. Below that depth, the ice is no longer brittle in the relevant sense. The stresses that would open a crack are instead accommodated by the slow plastic deformation we have already described, the migration of dislocations, the sliding of grain boundaries. Ice at 30 meters depth, under the pressure of all the ice above it, simply flows around an obstacle rather than fracturing against it. This is one of the most important boundaries in a glacier. The transition, somewhere between 20 and 40 meters below the surface, from the brittle upper zone to the ductile lower zone. Above it, ice breaks. Below it, ice flows. The boundary is not sharp, and its depth varies with temperature and flow rate, but it is real, and its consequences are written all over the glacier's surface. Where crevasse fields from different directions intersect, where the ice has been fractured both across its width and along its length, the surface is broken into a forest of isolated towers and columns of ice. These are seracs. They can be the size of houses or the size of apartment buildings. They are beautiful and genuinely unstable because the ice beneath them is flowing and deforming, and the crevasses defining their boundaries are slowly widening or narrowing as the glacier moves. Seracs topple without warning. They are among the serious hazards faced by mountaineers crossing glacier surfaces, and they fall not because they are pushed, but simply because the ice beneath them has flowed far enough that they are no longer balanced. The surface of a glacier also preserves a record of the glacier's history in a more literal way. Debris, rock fall from the valley walls, dust blown in from distant landscapes, the remains of animals that fell into crevasses centuries ago, accumulates on the surface and, more importantly, within the ice. In the accumulation zone, where new snow is constantly being added on top, older material is buried and drawn downward and inward into the glacier's interior. From there, it follows the ice on its long journey through the glacier's body. If you could trace the path of a single snowflake that fell in the accumulation zone of a large glacier, you would find it remarkable. It falls. It is buried. It is compressed into fern and then into ice. It sinks slowly, drawn downward by the weight of new snow above. Then it begins to move laterally, carried by the flow of the glacier toward the terminus. Deep in the glacier's interior, it moves faster than it did near the surface, because at depth, the internal deformation is greatest. It travels through darkness and pressure for years, decades, centuries. The ice around it recrystallizes, the grains growing and reorienting. And eventually, as the glacier thins toward its lower end, the snowflake's ice is brought back toward the surface, emerging at the snout of the glacier into the light, perhaps as meltwater, perhaps as a fragment of carved ice, perhaps simply sublimating into the cold air. The journey from snowfall to emergence at the snout of a large glacier might take 1,000 years. For the deepest ice in the Antarctic ice sheet, the journey from surface to base takes hundreds of thousands of years. The ice is patient in a way that is genuinely difficult to hold in the mind. Patient across timescales that dwarf entire human civilizations. And that patience, that depth of time encoded in the ice, is precisely what makes glaciers such extraordinary scientific archives. because everything that fell on the glacier, every molecule of ancient air trapped in every bubble, every chemical signature of every volcanic eruption, and every shift in ocean temperature, and every change in the composition of the atmosphere, all of it has been preserved, layered, and ordered, waiting to be read. In January 2004, a drilling team working at a remote location in East Antarctica, at a place called Dome C, reached a depth of 3,270 meters below the surface and pulled up a cylinder of ice that was, by their best estimate, approximately 800,000 years old. 800,000 years. The ice in that core fell as snow before our species. Homo sapiens existed. Before Neanderthals. At a time when the ancestors of modern humans were still living in Africa, making simple stone tools with no language in any form we would recognize. The world that snow fell into was a different world. And yet the snow was still there, compressed and transformed, but chemically intact, holding within it a record of the atmosphere and the climate of that ancient time. This is what ice cores do. They are drilled from the deep interior of the great ice sheets, where the ice is thick enough and cold enough and undisturbed enough to preserve hundreds of thousands of years of layered history. Each year's snowfall leaves a layer, and those layers, like the rings of a very slow tree, can be counted back through time. In the upper sections where annual layers are thick enough to distinguish, glaciologists can count them directly, year by year. Deeper down, where the ice has been compressed and the layers have thinned to millimeters or less, other methods are needed, matching chemical signatures to known events, like the sulfur spike from a large volcanic eruption, or using physical models of how the ice has flowed and thinned over time. Inside each layer of ice, there are two kinds of climate record, and they tell different parts of the story. The first is the trapped air bubbles. As we explored in the first chapter, these bubbles are sealed off as firn compresses into ice, and they contain samples of the atmosphere from the time of sealing. Typically a few decades after the snow fell, the lag introduced by the time it takes for firn to close its pore spaces. From these bubbles, scientists can extract the ancient air and measure its composition directly. They can measure how much carbon dioxide was in the atmosphere 800,000 years ago, how much methane, how much nitrous oxide. The results of those measurements are among the most discussed in all of climate science. What the bubbles show is that, across the 800,000 years captured in the Dome C core, the concentration of carbon dioxide in the atmosphere varied between roughly 180 parts per million during cold glacial periods and around 280 parts per million during warmer interglacial periods. That range, 100 parts per million, roughly, corresponds to the natural rhythm of ice ages driven by slow changes in the Earth's orbital geometry. The carbon dioxide and temperature rose and fell together in a long, slow dance, cycling through roughly 8 complete glacial-interglacial cycles in the 800,000-year record. The concentration of carbon dioxide in the atmosphere today is around 420 parts per million, higher than at any point in those 800,000 years of record. The second kind of climate record in the ice is subtler, and it requires a moment of explanation. Water molecules are not all identical. The oxygen atom at the center of each water molecule can exist in several forms, called isotopes, atoms of the same element with slightly different numbers of neutrons in their nucleus, and therefore slightly different masses. The most common form of oxygen has 8 neutrons and 8 protons in its nucleus, giving it a total mass of 16 units. A heavier, rarer form has 10 neutrons, giving it a mass of 18 units. Both are stable and both exist in ordinary water in a ratio that is very nearly fixed. But temperature changes that ratio slightly. When water evaporates from the ocean, the lighter molecules, those containing the mass 16 oxygen, evaporate preferentially because they require slightly less energy to escape the liquid surface. When that water vapor travels toward the poles and eventually falls as snow, it carries a slightly enriched proportion of the lighter isotope. And the colder the temperature, the more pronounced this enrichment, the more the heavy molecules have been left behind at the ocean surface, and the lighter the isotopic composition of the snow that falls. So by measuring the ratio of heavy to light oxygen isotopes in each layer of ice, a measurement that can be made on tiny samples with great precision, scientists can reconstruct the temperature at which that layer's snow fell. The ice is a thermometer, one that has been running continuously for 800,000 years. What those measurements show, in combination with the bubble records, is a detailed portrait of how the Earth's climate has moved through its glacial cycles. The temperature changes between a glacial maximum, when ice sheets covered much of the northern hemisphere, and an interglacial period like the one we currently inhabit, were roughly 4 to 8 degrees Celsius globally, though considerably more at the poles. Those changes unfolded over thousands of years, driven primarily by slow shifts in the Earth's orbit around the Sun. Changes in the tilt of the Earth's axis, the shape of its orbit, the timing of its closest approach to the Sun. Cycles that operate on timescales of tens to hundreds of thousands of years. The ice core records also capture shorter events with remarkable clarity. The eruption of the Toba supervolcano in what is now Indonesia around 74,000 years ago left a layer of sulfate in the ice. Smaller eruptions throughout history are recorded as thin chemical spikes, precisely dated. The onset of the Industrial Revolution appears as a change in the isotopic composition of carbon in the ice, as fossil fuels, which are depleted in a particular carbon isotope, carbon-14, because they are so old, began to be burned at scale. The record is not just about the past. It is a baseline, a calibration, a way of understanding what the climate system does naturally and at what pace. The natural transitions between glacial and interglacial periods, which look rapid in geological terms, unfolded over thousands of years. The ice core record does not editorialize. It simply shows the numbers quietly, layer by layer. And those layers are still being added to, right now. Snow is falling tonight on the Greenland ice sheet, and on the Antarctic plateau, and on the high mountain glaciers of every continent except Australia. Each snowflake carries within it the isotopic signature of the current atmosphere, the current temperature. In 10,000 years, if the ice is still there and someone is still looking, they will be able to read tonight's snowfall as clearly as we read the snowfall of 10,000 years ago. The ice remembers everything. It has always remembered everything. We are only now learning to read what it has kept. A glacier ends. Every glacier eventually reaches a place where the ice can go no further, where the warmth is too great, or the water too close, or the ice too thin to sustain its own flow. This is the terminus, the snout, the front. And what happens here is the final chapter of a journey that may have begun with a snowflake falling on a quiet mountain centuries or millennia ago. On a land-terminating glacier, one that ends on solid ground, the terminus is a place of constant melting. Ice arrives from above, carried by the flow, and it melts into streams that run out across the gravel and rock flour of the outwash plain below. In summer, these streams run grey and milky with rock flour, the finest product of the glacier's grinding of its bed, particles so small they remain suspended in the water rather than settling. This glacial milk carries the chemistry of the rock. The glacier has spent centuries digesting, and it feeds some of the most productive river ecosystems in the world. On a marine terminating glacier, one that flows into the sea or a deep fjord, the terminus is a different kind of place, and the physics of what happens there are considerably more complex. When a glacier reaches tidal water, the relationship between the ice and the ocean begins to govern how fast the glacier retreats. The most direct mechanism is calving, the breaking off of large blocks and slabs of ice from the glacier's front, which fall or slide into the water and become icebergs. Calving happens because the glacier is pushing forward from behind while the ocean water is offering no resistance in front. The ice at the terminus is effectively a cliff, sometimes tens or hundreds of meters high, and the stresses within it, the tension from the glacier pushing, the buoyancy of the water lifting the submerged portion, eventually exceed the strength of the ice. Fractures propagate and a section breaks free. The size and frequency of calving events depend on many factors: the geometry of the fjord, the speed of the glacier, the thickness of the ice at the terminus, and, increasingly important, the temperature of the ocean water lapping at the glacier's underwater face. Ocean water that is even slightly warmer than the melting point of ice can melt the submerged portion of a glacier's terminus at a rate that is far greater than surface melting from atmospheric warming alone. The glacier's front, below the waterline, is not a vertical cliff, but an irregular, often undercut surface, and warm ocean water circulating against it can remove ice from the base faster than the glacier can replace it from above. This undercutting destabilizes the terminus, making calving more frequent and more voluminous, which in turn removes the buttressing effect that the intact front was providing. The back pressure that was slowing the glacier's flow from behind remove that buttressing, and the glacier accelerates. It flows faster toward the sea, which delivers more ice to the terminus, which delivers more ice to the terminus, which calves more frequently. This is the mechanism that has been accelerating the retreat of Jakobshavnen and many other Greenland outlet glaciers in recent decades. The warming of subsurface ocean water in the fjords, water that originates in the Atlantic and has been intruding further into Greenland's coastal waters, has been eating at the glacier fronts from below, initiating the cycle of acceleration and retreat that is now well established in the satellite record. The loss of glaciers is measurable in many ways. Length, obviously, the terminus retreating up the valley year by year, the moraines it leaves behind marking its former positions like rings on a bathtub. Volume, the total amount of ice diminishing. And mass, the weight of water being added to the ocean, raising sea levels by amounts that are small on human scales but accumulating with each passing year. The glaciers of the world outside the great ice sheets of Greenland and Antarctica, the mountain glaciers of the Alps, the Andes, the Himalayas, the Rockies, the ranges of Central Asia, are retreating at rates that, in many cases, have no parallel in the ice core record, going back hundreds of thousands of years. Some will be gone within this century. The glaciers of the Alps have lost roughly half their volume since the mid-19th century. The glaciers of the Himalayas, which feed rivers that provide water to hundreds of millions of people, are thinning and retreating across nearly all of the range. And yet, and this is worth holding alongside everything else, the Earth has been here before. Not here, not this specific moment, not this specific combination of circumstances, but in ice and out of ice, in glacial periods and interglacial periods, through cycles of freezing and thawing that have repeated themselves many times over the past 2.5 million years, and through much longer cycles before that. The Earth has known ice sheets that buried what is now London under a kilometre of ice. It has known periods much further back when there was no permanent ice anywhere on the planet, when the poles were warm and the seas were high and forests grew where Antarctica now lies frozen. Ice comes and ice goes. On the timescale of the Earth, this is not a crisis. It is simply what the planet does, driven by the slow mechanics of orbital geometry, volcanic outgassing, the drift of continents, the opening and closing of ocean gateways that redirect the great currents of heat around the globe. Given enough time, tens of thousands of years, perhaps longer, the orbital cycles will shift again, the climate will cool, and ice will return to the places it is now leaving. The pace is the thing. The pace is what the ice cores make so plain. What is happening now is happening faster than the natural cycles, faster than the ice has retreated in the record that goes back 800,000 years. The natural world can adapt to slow change, because slow change leaves time for forests to migrate, for species to move, for river systems to adjust. Fast change leaves less room. But the ice itself does not hurry, and it does not worry. It does what ice has always done. It responds to the conditions it finds itself in, slowly, according to the laws of physics that have governed it since the first snowflake fell on the first cold mountain billions of years ago. Tonight, somewhere over the Greenland plateau, snow is falling. It is falling in the darkness, in air so cold and dry that each flake is tiny. The dry polar snowfall is nothing like the great wet flakes of a temperate winter. It falls through still air and settles on the surface of the ice sheet, adding another infinitesimal layer to a column of ice that goes down 3 kilometers below it. The snow that fell there last year is just beneath the surface. The snow that fell 1,000 years ago is somewhere in the middle, compressed and blue and carrying its tiny bubbles of medieval atmosphere. And at the very bottom, where the pressure is greatest and the ice is at its pressure melting point, the oldest ice is slowly, almost imperceptibly, deforming, its dislocations moving, its grain boundaries sliding, the whole deep mass of it leaning, very slightly, toward the sea. The glacier does not know it is retreating. The glacier does not know anything. It simply responds to weight and temperature and the patient insistence of gravity, as it has always done, as it will continue to do long after any of us are here to watch. There is something in that which is, if you let yourself feel it, genuinely restful. The ice is ancient. The processes that move it are ancient. The cycles of ice and warmth that the earth has moved through are so vast, so slow, so indifferent to the brief flicker of a human life, that to contemplate them is to feel, for a moment, very small and very quiet, not in a diminishing way. In the way that looking at a clear sky at night makes you feel small, a smallness that is also a kind of release. We are here for such a short time. The ice has been here for so much longer. And somewhere in that deep cold, in the blue silence 3 kilometers below the surface of Antarctica, there is ice that formed from snow that fell before our species walked the earth, ice that has been slowly moving, slowly flowing, carrying its ancient air in perfect darkness for 800,000 years. It is still moving now. And so we leave it there somewhere in that deep and patient dark. The day behind you is already distant. The ice is unhurried. Let yourself go still, the way the deep glacier is still. Moving, yes, but so slowly that stillness and motion are the same thing. Drift now, if you are ready. Sleep well.